Today's notes are on graphing log functions. Graphing log functions requires you to identify the inverse of the log, which will be an exponential function, find your ordered pairs or your parent function points from that inverse, and then you'll be reflecting or switching your x and y coordinates in order to graph the log function. Once you do a few of them, it will become easier and you won't have to do out all the steps, but at first you're definitely going to want to pay attention to how to find the inverse and the parent function and so on. Besides from that process, this also uses your transformations, so your left, right, up, down, reflections, and stretching and shrinking in the coordinate plane.
Before we go over the rules for graphing, let's refresh our memories on how to find the inverse of an equation. If I write out the steps for finding the inverse, the first step is always to switch your x and y variable. Once you do that, the second step is to solve for y. Starting with number 1, y is equal to log base 3 of x. I'm going to replace y with x. That means x is equal to log base 3 of y. In order to solve for y, with a log function, the only thing that you can do is convert to exponential form. So converting to exponential form indicates that we take the base of the logarithm, our solution of the logarithm as the exponent, and the argument as your answer. So 3 to the power of x is equal to y. This is our inverse. Y equals 3 to the power of x. The inverse is going to allow us to find the coordinates of the parent function. Number 2 is y equals log base 5 of x. We're going to switch x and y. X is equal to log base 5 of y. And we convert to exponential form. 5 to the power of x is equal to y. This is your inverse of the original function. The inverse relationship between exponential and logarithmic functions is also useful for graphing. We will be graphing log functions by graphing the parent function, then performing transformations. If we look at the general form of the log function, we have y equals log base b of x minus h plus k. The parent graph is just going to be y equals log base b, or whatever the base is, and then the argument of x. That is it. For example, if I had log, or y equals log base 2 of x plus 6 minus 2, we're looking for just y equals the logarithm, the base, and then that variable x. This is what you start graphing, and then the plus 6 and the minus 2 are going to be transformations in the coordinate plane. For the first example set, before we start graphing, the directions say to identify the parent function for the first step, and also to identify the inverse of the parent function. For number 1, your parent graph is y is equal to, or I should say the general form is y is equal to log base 7 of x plus 2. Your parent graph is log base 7 of x. If we take our parent graph and we find the inverse, that means we have to switch our x and y variables. And then we need to solve for y, meaning we have to convert to exponential form, or 7 to the power of x is equal to y. So the inverse of the parent graph is y equals 7 to the power of x. You might notice that there is a little bit of a trick or a shortcut to finding the inverse of the parent function. I'm not going to point it out because there's really no mathematical form of it other than you might just visually see what's happening there. So if you understand how to get to that faster, you wouldn't have to do this work off to the side. Number 2 is y equals log base 1/3 of x plus 4. The parent function is log base 1/3 and the value of x. And the inverse of this parent function. I know that it's going to be y equals 1/3 in parentheses raised to the power of x. You might have to work out the whole problem for the inverse, but that is what it will be, 1/3 to the power of x. The transformations are the same as what they've been all year. We have our horizontal shift, which is our h value. If you're subtracting h, you're shifting it to the right. If you're adding h, you're shifting it to the left. The a value is going to tell you if you're stretching or shrinking. In that case, you multiply the y values by a. If your a value is less than 0, it's telling you to reflect it across the x-axis. And also, if your x value is less than 0, you need to reflect your graph across the y-axis. So the second step is your stretch, shrink, or reflection. And the last step every time you're graphing is your up or down shift. If you are adding k, you're shifting up. If you're subtracting k, you're shifting down. You need to follow the transformations in the correct order, which is the order I just wrote them in. So horizontal shift, stretch, shrink, or reflection. Lastly is your vertical shift. I'm going to read through the steps as I go through number 1 for graphing. Number 1 for graphing is y equals log base 2 of x. And the first step listed above is to identify the parent function, which in this case is just the function I gave you. We don't have any transformations with this, but I'm going to write out each step. So this is step 1, the parent graph, which is y equals log base 2 of x. For step 2, you need to identify the inverse of the parent function. The inverse of this parent function is 2 to the power of x. Now, within step 2, I'm just going to add another little note that says make a table of values. And when you make a table of values, use the same test points that we used when we were graphing exponentials. So test your x values of -2, -1, 0, 1, and 2. So I'm going to come down to my function, and I am actually going to do that. So I'm going to use the inverse of the parent function, and I'm going to make a table of values. If I test -2 into my inverse function, the output is going to be 1/4. -1, the output is 1/2. 0, 1, 1, 2, 2, 4. Step 3 in the steps above tells us to reverse the x and y coordinates of the inverse. That means we're taking this graph here and we're switching our x and y variables. So switch your x and y values. That means I'm going to take this column for my y values, and I'm going to make that my new x value list. So 1/4 right here is my new x value. I'm switching these. In correspondence to 1/4, my new y value would be -2. If my y value was originally 1/2, that becomes my x value. My y value is -1. 1, 0, 2, 1, 4, 2. So at this point, which is step 3, all I did was switch my x and y values. And the last step, step 4, says to graph the log function and perform any indicated transformations. So when it says to graph the log function, you are graphing the parent function, which is these points right here, the points that you switched. So these ones are the super important coordinates. Graph those coordinates and then perform any transformations. That means I'm plotting a point at 1/4 -2, 1/2 -1, 1, 0, 2, 1, 4, 2. Previously, we graphed exponential functions, and exponential functions had a horizontal asymptote at y equals 0. Because we switched the coordinates, we actually switch everything about the function. So we took our inverse, which was an exponential of 2 to the power of x, we switched all those coordinates, and we end up with this graph. If we're switching the coordinates, we can also switch that horizontal asymptote, which now becomes a vertical asymptote. Log functions always have a vertical asymptote at x equals 0. If you're shifting this graph left or right, the vertical asymptote shifts with it. Also, the domain and range switch from the parent function or from the inverse parent function. So previously when we did exponential functions, our domain was all real numbers, but in this case, our domain is actually from our vertical asymptote of 0 to positive infinity, and our range was all real numbers, negative to positive infinity. So again, you find the parent function, you find the inverse of the parent function, and then you switch everything. You switch your x and y variables, you switch your asymptote, you switch your domain and range. Everything switches to give you the graph of your log function. Number 2, we have y is equal to log base 3 of x plus 1. Our parent function is log base 3 of x. The inverse of this function is y equals 3 to the power of x. If we make a table of values for the inverse, if we test -2, -1, 0, 1, and 2, we have outputs at -2, 1/9, -1, 1/3, 0, 1, 1, 3, 2, 9. Now we take these ordered pairs and we switch them, meaning you switch your x and y variables. The first point is going to be x coordinate 1/9, y coordinate -2, 1/3, -1, 1, 0, 3, 1, 9, 2. Now we're going to graph these as our parent function. I have a point at 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. That asymptote is at x equals 0, so I do not cross the y-axis, and that is my parent graph. Now the only other transformation included with this function is our transformation of shifting up 1 unit. I take my parent function, I shift every point up 1 unit. Shifting this graph up 1 unit will not change the vertical asymptote. That is still going to remain a vertical asymptote at x equals 0. It also does not change the domain or range. In this case, our vertical asymptote x equals 0. The domain is from 0 to positive infinity, and the range is negative to positive infinity. Number 3, y is equal to ln of x plus 4. Whenever we see ln, we know that's really log base e. Ln or log base e are the same thing. So I'm going to rewrite this as log base e, and I'm going to indicate that my parent function from this point is y equals log base e of x, of which I can find the inverse for. And the inverse is y equals e to the power of x. So knowing our inverse is e to the power of x, we can make a table of values. And you would need your calculator, or maybe some of you have that memorized, but most likely not. You're going to have to type in e to the power of -2, and your output is going to be 0.135. E to the power of -1 is 0.368. E to the power of 0 is 1. E to the power of 1 is 2.718. And e to the power of 2 is 7.389. Now that we have these points for the inverse function, you need to switch them for your parent function. Switching these points would give us a first point at 0.135, -2, 0.368, -1, 1, 0, 2.718, 1, and 7.389, 2. These are the points for my parent function, so I can go ahead and graph these on the coordinate plane. And just do your best, like 2.781 is somewhere in that area. 7.389 is around this location. Your asymptote is still at 0. That's your parent graph. Now we're not done until we do all of the transformations. The only transformation we see here is inside of the parentheses. So if it's inside of the parentheses, it's an h value. And in this case, we are shifting to the left 4. So not only did our graph shift left 4 units, but this is the first time we're seeing that the vertical asymptote also shifts left 4 units. So we can say our vertical asymptote is at x equals -4. The domain also matches that vertical asymptote, so the domain is from -4 to +infinity. And the range is negative to +infinity. Okay, check out my answer key on my website for the On Your Own section, and let me know if you have any questions.